Hi guys, my name is Melissa, and in today's video we're going to be talking about prime and composite. So to learn about what prime numbers are, a number with exactly two factors such as 1 and itself is called a prime number. And numbers that are prime are often called primes, and when a number has more than two factors, so more than 1 in itself, then it is not a prime number. And so let's take a look at an example problem. So which of the numbers below are prime? And so first we're going to write out our factor pairs. And so for 21, we have 1 times 21 and 3 times 7. For 22, we have 1 times 22 and 2 times 11. For 23, the only factor pair is 1 times 23. For 24, we have 1 times 24, 2 times 12, 3 times 8, and 4 times 6. For 25, we have 1 times 25 and 5 times 5. And so for a number to be prime, we can basically think of this as having one factor pair, and that factor pair would consist of the number itself and 1. And so the only prime number here would be 23. And so other numbers that are not prime, like 21, 22, 24, and 25, have more than two factors. So these numbers are going to be called composite numbers or composites. A positive number with more than two factors is called a composite, and 0 and 1 are neither prime nor composite. And that is because for 1, it's only 1 times 1, and 1 is itself, but that basically leads to one factor, since 1 is only going to be counted once, and so it doesn't have exactly two factors, and so 0 and 1 are neither prime nor composite. So our practice problem, the first practice problem says, is 39 prime or composite? So we're going to think about factor pairs for 39. We have 1 times 39, and then we have 3 times 13. So right off the bat, from 3 times 13, we know that there's more than two factors, so 39 is going to be composite. Now the next problem asks, is 47 prime or composite? So again, we're going to write out the factor pairs, and the only possible factor pair is going to be 1 and 47. 1 times 47, so the only two factors are going to be 1 and 47. So 47 is a prime number. Now 27 says, how many even numbers are prime? And so 0 is even, but again, we said that 0 is neither prime nor composite. And then the next smallest even number is going to be 2, and its only factors are 1 and 2. So that's going to be a prime number. But right after 2, we have even numbers like 4, 6, and so on. And all of the even numbers are divisible by 2. So all of them have 2 as a factor. So it has 1 itself, and it always has 2 and another number. So that means that 2 is going to be the only even number that is a prime number, and then every other even number is going to be composite, except 0. So 2 is the only even number that is prime, so it's going to be 1 even prime. And you guys should remember this concept, and so you guys should remember that there's only one even prime number, which is 2. The next problem says, circle all the prime numbers in the list below. So for 40, we know that factor pairs can be 1 times 40 and 2 times 20 and so on. So already there is another factor pair involved, so there's more than two factors, so 40 is a composite number. For 41, the only factor pair is 1 times 41, so there's exactly two factors, 1 and 41, so 41 is going to be a prime number. For 57, we're going to write out factor pairs, so we have 1 times 57, but then we also have 3 times 19. So right now we have more than two factors, so 57 is not a prime number, and it's a composite number. For 63, we have 1 times 63, 3 times 21, and so on. So again, more than two factors already, so it's a composite number. For 65, we have 1 times 65 and 5 times 13. So again, more than two factors already, so that's a composite number. And then for 79, the factor pairs are going to be 1 and 79 only. So 79 is going to be a prime number. For 1728, we can right away we know that it's divisible by 2 because it's an even number. So we're going to have 2 and another number. So this is going to be a composite number because it's an even number. Now in problem 29, it says circle all the composite numbers in the list below. So now we're circling composite numbers. For 29, we're going to list the factor pairs now. And so we have 1 times 29, and that's going to be the only possible factor pair. So that's a prime number. For 37, 1 times 37 is the only possible factor pair. So again, it's a prime number. For 42, we have 1 times 42, 2 times 21, and so on. So right away, we know that there's more than 2 factors, so that's going to be a composite number. For 49, we have 1 times 49 and 7 times 7. So we have 3 factors, 1, 49, and 7, and so that's going to be more than 2, so it's a composite number. For 51, we have 1 times 51, and then we have 3 times 17. So right away we have more than 2 factors, so that's going to be a composite number. For 59, we have 1 times 59, and then that's going to be our only factor pair, so that's a prime number. And for 395, we have 5 times 79, and so right away we have more than 2 factors, so that's going to be a prime number. And so the only composite numbers here are going to be, 395 is a composite number because it has more than 2 factors. Sorry for the confusion. So 395 is a composite because it has more than 2 factors, so it's going to be a composite number. And so out of the list in problem 29, the possible composite numbers would be 42, 49, 51, and 395. Now in problem 30, it says exactly 9 primes are less than 25. List them in order from least to greatest. Now we know that 0 and 1 are neither prime nor composite, so we're going to start with 2. And we know that 2 is a prime number because its only factors are 1 and 2. Then we have 3 because its only factors are going to be 1 and 3. 4 doesn't work because its factors are 1, 2, and 4, so it has more than 2 factors. 5 is only 1 and 5, so it has 2 factors. 6, we have 1, 2, 3, and 6 as factors, so there's more than 2. Now we have 7, the only factor pair is 1 times 7, so there's only 2 factors involved. Then 8, we have 1, 2, 4, and 8 as factors, so there's more than 2 factors. For 9, it has 3 factors, 1, 3, and 9, so it's not a prime number. 10, not a prime number because it has more than 2 factors. 11, the only factors it has is 1 times 11, so it's self and 1, so it has 2 factors only, so it's prime. Then 12, it's already divisible by 2, so it has more than 2 factors. 13, the only possible factor pair is 1 and itself, 1 times itself, so it has exactly 2 factors, so it's a prime number. 14, we can divide it by 2, so we have 2 and 7 as a factor as well, so there's more than 2 factors. Then for 15, we have 3 and 5 as factors as well, besides 1 and itself, so it has more than 2 factors and is therefore not a prime number. Then 16, we have 1, 2, 4, 8, and 16, so more than 2 factors. 17 is going to be 1 and 17 only, so it has exactly 2 factors. For 18, it's already divisible by 2, so we have 2 and 9 besides 1 and 18, and we also have 3 and 6, so there's more than 2 factors, so 18 is a composite number. Then we have 19, where 1 and itself are the only factors, so it's a prime number. And then 20, it's divisible by 2 and a lot of other numbers as well. So it has more than 2 factors. And then we have 21. It has 3 and 7 as a factor. So it has more than 2 factors because it has 1, 3, 7 and itself. 22, also divisible by 2. So it has 2 and 11 besides 1 and itself. So it's not our prime number. Then we have 23, which only has 1 and itself as a factor. Then 24 divisible by 2 and 25 is divisible by 5. So both of them are composite numbers. And so we have exactly 9 primes that are less than 25, being 2, 3, 5, 7, 11, 13, 17, 19, and 23. Now let's move on to the next page. And so here we're going to learn about factors, and we're going to learn an activity called sieve of Eratosthenesis. And so for problem 31, we're completing a grid of numbers. So we're basically learning about an algorithm. And so the algorithm that we're going to learn is called the sieve of Eratosthenesis. And we're using these steps to identify primes between 2 and any number. So let's look at how we do this. So first we start with the grid of numbers and perform the following process to identify all primes less than 100. So first we're going to circle the smallest number that is not already circled or crossed out. Then we're going to cross out all of the multiples of the number you circled in step 1 except for the circled number itself. We're going to repeat steps 1 and 2 until every number on the grid is either circled or crossed out. And so let's take a look at problem 32. Well, we're first going to look at problem 31. And so we're going to circle the smallest number that is not already circled or crossed out, and so that's going to be 2. Then we're going to cross out all of the multiples of that number except for the circled number itself. So we're going to cross out multiples of that. So all 10s are multiples of 2. So all even numbers are basically multiples of 2. So we're going to cross them out. And then it says repeat steps 1 and 2 until every number on the grid is either circled or crossed out. So then the next smallest number that's not already circled or crossed out is going to be 3. And then so we're going to cross out all multiples of 3. Some might have already been crossed out, but I'm just going to recross it out just to make sure that I don't get mixed up with the multiple countings. So we're just going to cross them out. We're crossing out multiples of 3 right now. And then the next smallest number that's not already crossed out is going to be 5. And so we're crossing out multiples of 5 now. Then the next smallest number that's not already crossed out is going to be 7. So now we're going to cross out multiples of 7. So we're crossing out multiples of 7 right now. And then the next smallest number that's not already crossed out in the grid is going to be 11. So now we're going to cross out multiples of 11. They're already all crossed out. Then the next smallest number is going to be 13. Now we're going to cross out multiples of 13. So 13, 26, 39, 52, 40, 65, 78, 91, and yeah, then the next smallest number that's not already crossed out is going to be 17. And so now we're going to cross out multiples of 17. So it's going to be 34, 51, 68, and 85. Then the next number that's not already crossed out, the smallest one from there, is going to be 19. And so we're now going to cross out multiples of 19, starting with 38, 57, 76, and 95. Then we're going to do the next smallest number that's currently not crossed out, and that's going to be 23. So we're running out of colors right now. We'll select 23. So we're going to now cross out multiples of 23, like 46, 69, 92. Then the next smallest number that's not already crossed out yet is going to be 29. And so we're going to cross out multiples of 29, like 58 and 87. Then the next smallest number that's currently not crossed out is going to be 31. Now we're going to cross out multiples of 31, like 62 and 93. Then we're going to go ahead and circle 37 because it's currently not crossed out and it's the smallest out of the ones that are not crossed out. So now we're going to cancel out or X out multiples of 37, starting with 74. Then we're going to circle 41 because it's the smallest number right now that's not currently X'd out. And so we're gonna X out multiples of 41, like 82. And then we're going to circle 43 because it's currently the smallest out of what's not crossed out. Now we're going to X out multiples of 43, like 86. Then we're going to circle 47 because it's not crossed out yet and it's the smallest out of what's not crossed out. And we're going to X out multiples of 47, like 94. Then we're going to circle 53 because it's the smallest of what's not crossed out yet. And then we don't have any multiples of 53 in this grid anymore because a multiple of 53, the smallest multiple is going to be 106, which is outside the grid. And so that means that any number that's larger than 53, it's not going to have multiples in the grid. So basically they're all going to be circled. And so it says how many primes are less than 100. I know this took a really long time, but we're going to count how many circles we have. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and 24 circles. So that means that we had 24 so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have 25 primes that are less than 100. And then it says, what is the largest two-digit prime? So the ones that we circled are prime numbers, and so we're going to look for the largest prime number, and that is going to be 97, which is the largest out of the numbers that are circled. Then what is the most common units digit among the two-digit primes? So among the two-digit primes, we're going to look at the units digit. And so among the 21 two-digit primes, 5 have units digit of 1, like 11, 31, 41, 61, 71. So the units digit is 1 in this case, and the units digit is going to be 2 for the next column. Units digit is going to be 3 for this column, 4, 5, and so on. And so for units digit of 1, we have 5 prime numbers. For 2, we have 1. For units digit of 3, we have 7 prime numbers, 0 for 4, and 1 for 5, 0 for 6, 6 for 7, 0 for 8, 5 for 9, and 0 for 0. And so, with 7 being the greatest, the most common units digit was going to be 3. Then our next problem asks, Lizzie subtracts 1 prime from another and gets 21. What will Lizzie get when she adds the same 2 primes? So we're going to look for 2 primes that have a difference of 21. And so that's going to be and also based on the pattern of like adding odds and evens and looking at differences between odd numbers and even numbers from previous videos, we know that the difference between an odd number and an even number, so it can be vice versa because we're doing differences. So differences are going to be odd when we have one odd and one even number involved. And so since the difference between 2 prime numbers is 21 and 21 is an odd number, that means that 1 even prime number was involved and 1 odd prime number was involved. And so we know that the only even prime number is going to be 2. And so 2 is going to be 1 prime that's involved. And for the difference to be 21, we know that the other prime must be 23 so that the difference can be 21. Now when we add these 2 primes together, we get 25. Now let's look at the next page. For problem 36, we have something called twin primes. And twin primes are pairs of prime numbers that differ by 2. For example, 41 and 43 both are prime numbers and the difference is 2, so they are twin primes. How many pairs of 2-digit twin primes are there? So now we're going to look at our grid. And so the pairs of 2-digit twin primes are going to be 1 and 3. 11 and 13. We have 11 and 13, 17 and 19, 29 and 31, 41 and 43, 59 and 61, and then we also have 71 and 73. Again, you guys can go pause the video and then check with the grid, and that is going to be 6 different pairs of 2-digit twin primes. So I'll write 6 pairs. Now in problem 37, an MRIP is another special type of prime. When the digits of an MRIP are written in reverse order, the result is a different prime number. For example, these numbers are going to be 13 and 31, where the result is a different prime number and they're in reverse order. Now, although things like twin primes might be useful, not all of these names of primes, like the Mersenne prime, Sophie Germain prime, Einstein prime, you guys do not have to know these. And the fundamental idea that you guys must know, however, is the concept of prime and composite numbers, but you guys don't really have to know all of these terms. And so again, going back to problem 37, the pairs of MRIPs are going to be 13 and 31, which is given. So I'll write 13 and 31. We also have 17 and 71, 37 and 73, and 79 and 97. Now we'll look at what a Sophie Germain prime is, and that is basically a prime P such that 2 times P plus 1 is also a prime. And so for example, 3 is a Sophie Germain prime because 2 times itself, so 2 times 3 plus 1 is also a prime. And so to find the Sophie Germain primes that are less than 50, we're going to look at the results when we multiply each prime that is less than 50 by 2 and then add 1, which is what 2 times P plus 1 indicates. So we're first going to list all the primes that are less than 50. So we have 2, 3, 5, 7, and then 11, 17, 19, 11, right. So we're just listing all of these. And right here, I don't know why there was X sign there, but 13 is a prime number, you guys. And so anyways, we have 13, 17, 19, 23. We're just listing out prime numbers that are less than 50 so far. That's going to be it. And then we're going to try multiplying these numbers by 2 and adding 1. So 2 times 2 plus 1 is 5. I'll just write it above. 3 times 2 plus 1 is 7. 5 times 2 plus 1 is 10 plus 1, so 11. 7 times 2 plus 1 is 15. 11 times 2 plus 1 is 23. 13 times 2 plus 1 is 27. 17 times 2 plus 1 is 35. 2 times 19 plus 1 is 38 plus 1, so that's 39. 23 times 2 plus 1 is 47. 29 times 2 plus 1 is 58 plus 1, so it's 59. 31 times 2 plus 1 is 62 plus 1, so it's 63. 37 times 2 plus 1 is 74 plus 1, so 75. 41 times 2 plus 1 is 82 plus 1, so 83. 43 times 2 plus 1 is going to be 86 plus 1, so 87. And 47 times 2 plus 1 is going to be 94 plus 1, so 95. Out of these, we're going to see which of the results, so 2 times p plus 1 is actually a prime. So it's going to be 5, 7, 11, 23, 47, 59, and 83, 87. And so we're going to circle the prime numbers that made the results, but also a prime number. So those are going to be 2, 3, 5, 11, 23, 29, and 41. Right, also 87 is not a prime number, so that would not be circled. Sorry for the confusion. But 87 is not a prime number because it can also be divided by 3, since 87 divided by 3 is going to give us 29. And so we're going to write out our answer in black. So it says list all the Sophie Germain primes that are less than 50. So those are going to be 2, 3, 5, 11, 23, 29, and 41. Now we'll look at the next problem. So an Einstein prime is a prime number that is 1 less than a multiple of 3. So for example, 71 is an Einstein prime because it's 1 less than a multiple of 3. So a multiple of 3 would be 72, 3 times 24, and it's 1 less than that. And so it says list all the Einstein primes less than 100. So in this case, we subtract 1 from the first few multiples of 3. And so for example, multiples of 3 like 3, 6, and 9, we're going to subtract 1. Gives us 2, 5, and 8. And so the prime results are going to be 2 and 5. And so we should notice that the result of subtracting 1 from an odd number, like 3 or 9, is always going to give us a prime, result. And so, So what we should notice, sorry for the confusion, let me say that again. So we should notice that when we subtract 1 from an even number, when we subtract 1 from an odd number like 3 or 9, it always gives us an even result like 2 or 8. So we're not going to find any other Einstein primes by subtracting 1 from an odd multiple of 3 because it's always going to give us an even number. And an even number is not going to be a prime because it can already be divisible. It can already be divided by 2, so that indicates that it's a composite instead of a prime. And so the next largest even multiple of 3, since we're not doing odd multiples anymore, is going to be 102. But then that's bigger than 100. So Einstein primes. So now we're going to consider even multiples of 3 that's less than 100, since we know that multiples of 3 like 102 or 105, these are all greater than 100, so we need to make sure that the numbers are less than 100. And so now we're going to consider even multiples of 3, since we know that odd always gives us an even result, and we're going to make sure that it's less than 100. And so we're going to look for even multiples of 3 that's less than 100. For example, like 12, 18, 24, 30, 36, 42, 48, 54, 60, 63, 60, then 63 is odd, so 66, 72, 78, 84, 90, and then 96. And so we're going to test those out. So we're going to subtract 1 and then divide it by 3 to see if it's a prime number. And so 12 minus 1 divided by 12 minus 1 is 11. Right, so it's 1 less than a multiple of 3. So these are all multiples of 3, so we're now going to subtract 1 to get the prime number. It's going to be 11, 17, 23, 29, 35, 41, 47, 53, 59, 65, 71, 77, 83, 89, and 95. So of these, prime numbers are going to be 11, 17, 23, 29. 35 is not a prime number because it can be divided by 5. 41, 47, 53, 59, 65 can be divided by 5, so it's a composite. 71, 77 can be divided by 7, so it's a composite. 83, 89, and 95 can be divided by 5, so it's a composite. And so we're going to list the Einstein primes now, so those are going to be 2 and 5. So we're going to include the 2 and 5 that we found previously, like 2, 5 here. Then we now write these out. 11, 17, 23, 29, 41, 47, 53, 59, 71, 83, and 89. Now we're going to look at one more. So we're going to learn about a Mersenne prime. And a Mersenne prime is a prime number that is 1 less than a power of 2. But right now, we're not going to go over a Mersenne prime because I'm not sure if you guys learned about powers or not. And so I think we're going to introduce powers later. So we're going to skip Mersenne prime for now, and then we'll talk about Mersenne primes later on when we talk about powers. And so yeah, that was it for today's lesson, and I'll see you guys in the next video.